small correction. My name is Xin Li from Nanjing Joint Institute for Atmospheric Science. My professor, Dr. Xiaolei Zou, she's from Nanjing University of Information Science and Technology. I'm very honored here for this talk.
Sorry.
Not at all. The topic is several measures for improving the CrIS sky infrared radiance assimilation, which is our recent process. This report includes 4 parts. First, we review the current difficulties of infrared data assimilation in cloudy regions. We know both the radiative transfer model and the NWP microphysics have uncertainties. So it leads to mismatch between the observation and the TB simulations. Also, on the all-sky condition, the tangent linear of observation operator strongly depends on the accuracy of the initial state. So we think the all-sky TB simulation is very important. Let's see, in addition to the clear sky RTM model, the absorption and the scattering are also considered in the all-sky simulations, depending on the relative size between the wavelengths and the particle radius. Let's take the plane parallel atmosphere as example. The TOA radiance are consistent of the upward emission of the atmosphere above the world, the upward emission of the cloud top, and the transmission of the radiation under the cloud. So one key point is to calculate the cloud optic depth. Our research is based on the CRTM. The cloud variables are cloud contents and effective radiance for cloud water, rain, ice, snow, and groundwater. The cloud optical depth is calculated based on the lookup table. The extinction coefficient and the single scattering albedo are dependent on the wavelengths and the effective radiance. The extinction is divided into the absorption and the scattering. Finally, the COD is adjusted after the forward scattering adjustment. So second, we investigate the influence of the microphysics on all-sky TB simulation. We focus on the CrIS, a hyperspectral infrared instrument on board the Sumi MPP satellite. It is a cross-scan sensor. The spectrum covers the long wave infrared radiance, middle wave infrared radiance, and the short wave infrared radiance. To simulate the all-sky radiance, we use the Wolf model forecast as input. 3 microphysics schemes are evaluated, including the WSM6, Thomson, and the Morrison. We can see several different features among these 3 schemes. The first uncertainty is the cloud top. We can see compared to the BIAS level 2 product, we see the Thomson and the Morrison experiments show higher cloud top than the WSM6. We see the second uncertainty. It's the vertical distribution of cloud content. It influences the calculation of cloud optical depth. Thomson is dominated by the snow at up levels, but very little ice. And the Morrison has higher ice top than the WSM6. The third uncertainty, we diagnose the effective radiance according to the assumption of the microphysics scheme. We can see the size sorting features for ice in the Morrison scheme, but the vertical homogeneous features in the WSM6. For snow, they have very similar features among the 3 schemes. Okay, let's see how these difference among microphysics impact the TV simulation. A window channel of CrIS is selected. Compared to the observation, we see the simulated brightness temperature is higher in WSM6. Other two schemes are better. We can see from the demand averaging the cloud optic depth profile. It is because the magnitude because the magnitude is larger in the Thomson and Morrison than the WSM6. Also, the cloud top is high. From the long period statistics, we see negative bias in WSM6 experiments under all sky condition. When we consider different cloud types, we see different bias features between the thick cloud, for example, cumulus, and the thin cloud, for example, cirrus. Also, for the thick cloud, we see the O-B bias is linear correlated to the bias of the cloud top. But for thin cloud, the cirrus cloud, we see it is not correlated. It may also related to the cloud optical depth. Also, we checked the different synoptical cases. Differences are many from among microphysics schemes rather than different cases. So we think it indicates that the bias results above is a general conclusion. For the third part, we propose a modified observation area scheme for the cloudy radiance. We all know there's a widely accepted observation area adjustment scheme which uses the symmetric cloud effect parameter. We can see some works from here and Okamoto. However, from our previous results, we see different bias under different cloud types, no matter in WSM6, Thomson, or Morrison. We believe that the cloud effect parameter, which is used to predict the O-B standard deviations, should also consider different cloud types. For example, we see the parameter on the series increase rapidly, but very slowly under cumulus cloud. So we propose a cloud type dependent cloud effective parameter. We see the traditional scheme, the blue curve. We see the O-B close to Gaussian distribution under the whole sky, but not under individual cloud types. If we use the modified scheme, the red curve, we see the O-B close to the Gaussian distribution, not only on the whole sky, but also on each cloud top, under each cloud type. In our previous works, we bias correct the simulated TB and adjust the observation area. It is on the hypothesis that we assume the model predicted cloud field are reasonable. However, if they are not reasonable, in the first part, we propose a modified all-sky TV simulation scheme with the background cloud field constrained by the microwave cloud information. Because we think the microwave can penetrate the non-precipitation cloud, we think it may improve infrared TV simulation. For the 3 MPV satellites, the ATMS and the CrIS observe the Earth simultaneously. We think we can improve the CrIS TV simulation with the help of the ATMS. So we want to use the microwave retrieve the liquid water path, ice water path, and the rainwater path to constrain the model 3-dimensional hydrometers. So how to do it? We use the GSI data simulation system. We developed the observation operators for these water passes. Since the cloud field change rapidly in space and time, the flow-dependent background error providers should be considered. We use the hybrid ensemble variational schemes, also added the QR, QIS, QSNO, and QGraph as the analysis variables. We see the system check. First, the covariance are checked by the single point test, simulation test. It is a typhoon case. We can see the increments show the vortex pattern. The second one, the agent test is performed to guarantee the correctness of the observation operator. The third one, we use the disclosure method to diagnose the observation error for these water passes. We also separated treat them under the ocean and the land. Let's see the performance. Before the CRTM simulation, the cloud background, for example, the cloud ice, are improved by assimilating the ATMS cloud water paths. It is a May rainfall case in China. We can see from the QI's increment, the red indicates the increase and the blue indicates decrease. We see the up-level ice clouds are enhanced near the coastline of the South Ocean, but weaker along the May front. How this change of background cloud field impacts the CrIS TB simulation? It is a long wave window channel. The TB simulation with the default scheme is significantly higher than the observation in the South Ocean area, but lower in the area of the front. It is due to the much weaker cloud scattering over South Ocean and much stronger over the area of the front. When we use the modified scheme, the cloud background is constrained by the microwave retrieved cloud. We see the simulated TB are much better in these two areas. So we see the long period statistics. The left are bias and the right are standard deviations. First story, long wave, middle wave, and the third row is the short wave. With the help of the new O-sky simulation scheme, we found the green color, the O-B bias are reduced by about 50%, and the standard deviations are reduced by about 25%. Though they are not the same among different spectral bands. Finally, we see the probability distribution. It shows that with the new scheme, data counts of O-B less than 10 Kelvin are increased. It means the effective data in the O-sky data simulation will be potentially increased. So in the next step, we will try to improve the O-sky CrIS infrared data simulation with the scheme constrained by the microwave cloud information. Okay, there's the summaries for this talk. Maybe the time is up. If you are interested in our studies, please refer to these two papers published on monthly review. So, dear professors and researchers, thank you so much for your attention. This is my email address. Thank you.
Thank you, Xin, for your great presentation. I will check if we have questions. Okay. Javier is just typing a question. Yeah, okay. Javier's question is, can you mention more about the cloud type dependent parameterization?
Okay, let's go through the slides. So this one. Actually, in the default automatic scheme, they bias correct the bias and the normalized the standard deviation under the O-sky condition. But in our scheme, we divided different conditions. For example, the serious cloud, the cumulus cloud, and and so on. Individual, we calculate the bias and the standard deviations for these individual cloud types. So we calculate when we do the bias correction and the normalize, we use the bias and the standard deviation under the individual cloud types. We think it may improve further the Gaussian distributions on the individual cloud type. So that's all.
Okay, thank you. Another question by Xiaoyan Zhang. Have you evaluated Assimilate O-sky Radiance data comparing Assimilate star LWP data, which one is better?
It's a very good question. So it faces a question that how we assimilate the satellite cloud observation. One method is to assimilate the old sky TB. Another is to assimilate the retrieved satellite product. I think my work the purpose of my work is to improve the old sky TB simulation. I focus on the improvement of the background field of the current model predictions. But I also evaluate the performance of the assimilating LWP or IWP, focusing on the forecast of such typhoon or convection. I think maybe the retrieved assimilation, it depends on how can we quantify the observation error for the retrieved LWP or the IWP. I'm not very sure which is good.
Okay. Yeah. One more question from. Oh, okay. Two more questions. Okay. One more question from Prashant. Why retrieved MW parameters are important in place of MW all sky data simulation joined with IR all sky? This.
I think maybe the most challenging thing for improved all sky TB simulation is that there is maybe uncertainties in model predict cloud field. So we want to find a way to improving the model predict cloud field. But we want to find some independent or valuable sources for these cloud informations. We think the microwave can penetrate non-precipitation cloud, so it may sense the cloud information more clearly than the infrared. So we combine use the information for IR. Another reason we think because they observe the Earth simultaneously, so we can see the combination easily for these two instruments. So
okay, yeah. We still have time for one more question. One more question and comment from Matsia. Do you use outer loop in the variational data simulation system? That might be the solution to improve background rather than using retrieved microwave parameters.
Yeah, outer looper. I think it is very important because for the nonlinear operators such as all sky simulation. But I think in our experiments, we use the microwave retrieved constraint. Also use the outer loop. Yeah, for the ice water parts, liquid water parts, we also use the outer loop. I'm not sure because I have not tried only use the outer loop based on the model predicted cloud information to simulate.
It partly combined with the ensemble based.
Yeah. Yes.
Yeah. Okay, I think if there is no more questions, let's thank you, Dr. Xin Li, again for your great presentation. Thank you.